Hello, students. In the virtual lab that you guys had with the bending light, what we found is that when the laser pen is upright, right like this, that's what we would call the normal. So this dashed line right here, that would be a line that is perpendicular to the surface or the boundary between two different materials. So as we move away from the normal, now this is a little confusing for some. We don't measure the angle from the actual boundary itself. When you're measuring the angle of reflection, you have to go off of the normal. So when I put my protractor up onto the border here, or my boundary and my normal, as I move away from the normal, so right here I'm moving it away 20 degrees away from the normal, that angle of reflection right here, we're going to follow the law of reflection, and you're going to notice on the right hand side, if I had this positioned a little better, that the angle of reflection is 20 also. Now what you are going to notice is that the angle of reflection is always the same as the angle of incident. The incident is the incoming ray right here to the boundary. It's the same as the reflected ray right here. Underneath that, if we're going from a material that is less dense, like air, to a material that's more dense, like water, you're going to see that the light is going to bend towards the normal. All right. Now, why does it do that? You could think of this as a toy car that's racing across a surface, and let's say it's coming right along like this. Now, when it strikes carpet, let's say that the blue down here is a carpeted region. When it strikes the surface, the right tire of the car is going to hit the surface of the carpet first, and it's going to slow that right tire down, whereas the left tire on the other side is still going to be moving pretty quick. So the car is going to turn to the right in this case. Now, that bending, that turning of your car, the bending of the light, is what we call refraction. Now, the amount of bending that's going to occur, that's going to depend on our index of refraction of our materials. Again, we can think of this as a car moving across a tiled surface, okay? And then a car moving through a carpeted surface, something that would be more dense. So it's going to change that direction of that light. That's called refraction, the bending of that light. Now, in the simulation, I said that you didn't have to be very specific with this angle of, well, actually, I didn't even say you had to be very specific with the angle of reflection angle of reflection or angle of incident. And I definitely didn't say that you had to be specific with this angle of refraction. But today, we are going to be specific with it, because instead of us just reading these numbers, we're going to calculate that mathematically. Now, in order to calculate this mathematically, we need to have a formula. The formula we're going to use is called Snell's law. Now, Snell's law requires us to have a couple of things known. We have to know our angle of incident. So if we know that this is exactly 20 degrees, then great, we know what that's going to be. All right, we need to know the index of refraction for each of those materials. So air is always going to be 1. Water, in this case, is 1.33. But if we change the density of water, we changed it to, let's say, salt water, that's going to change our density down here to be greater than 1.33. Or if we change this to glass, if we change it to glass, our index of refraction is going to be 1.5. So we have to know those items. We have to know the angle, and then we have to know the angle of incident, and then we have to know the index of refraction for the two different types of materials. So what we're going to do now is we're going to flip over and we're going to look at some problems using Snell's law. All right, so Snell's law, and this is what you have to have on your paper. Just go ahead and edit it right inside of Cami. So Snell's law. We're looking at a formula where we're going to have n. Now the n is the index of refraction that I was talking about. We're going to use some trig here. We're going to say sine theta of our first material. So that would be of our first material. That would be, let's say, the air. Then that's going to equal N2. What's the second material? Is it going into water? Is it going into air? Is it going to be going into glass? So you'd have to know that index of refraction for that second material times sine theta. That would be the angle of refraction right here. So let's work this out. All right, I'm going to leave this up here. We'll get rid of this to make it a little bit cleaner. We know that this angle right here, this 45 degrees, is the angle of reflection. We know that it's going to be that. Okay, so that's 45 degrees. So I can put down sine 45 degrees equals, I need to know what the index of refraction for this material is. Well, it says N1. Now that N1, that's the index of refraction for it, and that is 1.5. So I'm going to put 1.5 right out in front. So we're going to multiply those. That's going to equal, all right, now we have this angle. This is the angle of refraction. All right, so the angle of refraction, how much bending is going to be occurring? Now, we can interpret one thing right away. In the example that I showed you earlier, we went from something that's less dense to more dense, and the refracted ray bent towards the normal. This one is bending away from the normal. So before we do any math, we should already identify that this guy right here, my index of refraction, is going to be less than this one right here because it's bending away from the normal. All right, so we're going to say N, because we don't know what that index of refraction is. That's what you're trying to figure out. Equals sine of 65 degrees. Okay, so how do we figure this out? Well, we need our calculator. So if we get our calculator handy, we can put this in. We're going to go 1.5 times sine 45, and I'm going to close that, equals. We divide that value by sine 65. So all you have to do is follow the formula. Why am I dividing by sine 65? Because I need to get this to the other side. So if I'm multiplying it by n, I have to divide it to get n by itself. So we'll divide that. We hit enter, and the index of refraction for that second material is going to be a 1 point, and let's go 2 places past it. We could just go to 1 place past the decimal, 1.2. All right, so there's our answer for the first one. It doesn't get any more difficult than that. You just have to get used to what the terms are for these. So let's go on to the next one down here. It says, for the drawings below, state whether N1 is bigger than N2, or if they're equal. Remember, from the top one, I see that the angle of incident is 45 degrees. The angle of refraction bent away from the normal. So that told me I was going from something that is going to be more dense to something that is less dense. If it bends away from the normal, it's going into a material that is less dense. It'd be like going from carpet onto a tiled surface, or in this case, 1.5 is usually what we'd use for us describing glass. And the 1.2 might be going into, let's say, something in between water and maybe ethyl alcohol, something like that. I don't know the index of refraction for ethyl alcohol, but it's got to be somewhere in between there. All right, let's look at the examples here. So number 2A, I see the angle here, and then if I'm comparing it to this one right here, my angle increased. So if the angle increased, is that going to be going into a more dense or less dense material? That's just like what we had for number 1. So the N1 in this case, this guy would have to be N1 is going to be larger, and then N2 is going to be smaller. Okay, see how these go? Then when we have letter B, you can see that here my angle of incident is larger than the angle of refraction. So I'm going to let you figure those out, or for that one out. And then for letter C here, you can see my angle of incident and my angle of refraction, that they're going to be the exact same. So what can you interpret from that? You put your answers down, and then we're going to go on to these down below here. All right, so I'm going to clear my calculator. We have a list or an index of refractions for different materials. So I have a ray of light traveling from air. All right, well, air, our index of refraction for it is 1. So I'm going to put right here, I'm going to put N equals 1. And it's going to go into crown glass. Now, crown glass is going to have an index of refraction of N of 1.523. All right, now those are on the data table. You wouldn't have to write them down, but I'm just keeping track of it. It says that the light is going to strike the surface at an angle of 30 degrees. Well, that is the angle of incident. Okay, that's the angle that it's coming into the boundary between that air and crown glass. What will be the angle of refraction? So let's put our pieces of the puzzle together. Again, Snell's law, N1 sine theta 1 equals N2 sine theta 2. All right. We'll go ahead and start plugging our stuff in. We have N1, that's going to be 1, times sine. Now our angle of incident was 30 degrees, equals, we have N2, that's the index of refraction for crown glass, is this. And then we're going to go times sine, and then we don't know what that is. All right, we're going to hop over to the calculator. Something I didn't mention before, make sure your calculator is in degrees. All right, it has to be in degrees. If it's not in degrees, you're not going to get any of this right. So how can we work this out? Well, I'm going to put in the information as I see it right here, but I need to get the angle right here. So if you have to get the angle, remember from before, you need to do inverse sine. I would really suggest that you rearrange your equation first before you start plugging it into the calculator, because we know that we have to find that sine theta, the angle, not the trigonomic value. We want to find the angle of this. So I would have to divide both sides by 1.523. Okay, so if I divide both sides by that, that goes away from that side. Then if I want to get just the angle right here, if I just want the angle, I have to do the opposite of a sine, which would be the inverse sine. So that's where we're going to have to use our calculator. We're going to go shift, or maybe that second button, depending on your calculator, sine, and then we're going to plug in this information right here. So to get rid of that sine, right here, we are going to do inverse sine. All right, so I have 1 times, oh, I didn't put the 1 in there. We go 1 times sine 30, close that thing, you gotta close it, divided by 1.523. And then I'm gonna close that one. I hit equals, and the angle that I'm looking for here, the angle of refraction, is 19 point, let's round it off, 19.2 degrees, right like that. All right, pretty straightforward. You just have to make sure that you use your calculator correctly. And since we have done the trigonometry stuff from the vectors, everybody should have this memorized. Everybody should be able to plug this stuff into a calculator, right? So we're going to go to the next question. So let's go to question number 2. Question 2, light traveling through air encounters a second medium which slows the light to 2.7 times 10 to the 8th meter per second. What is the index of the second medium? All right, so we need a formula. I was hoping we wouldn't have this, but we've got it. So we need to look at how we calculate that index of refraction. All right, so I have n, index of refraction. What we're going to do is we're going to put in the speed of light, 3 times 10 to the 8th meter per second. All right, so that we could label that as c because that's the variable that we always use for that. We're going to divide that by the velocity of our medium, all right, of the light in that medium. So we have divided by 2.7 times 10 to the 8th meter per second. So we can figure out what our index of refraction for that second medium would be. So we've got, let's put this into the calculator. You go 3 EE8, that is the speed of light in a vacuum. We go divided by 2.7 EE8 equals, the index of refraction here would be let me change my color here. We're going to go 1.11. That's our answer. All right, so we have two formulas. We've got our Snell's law here, and then we need to make sure that if we are trying to calculate from the velocities what the index of refraction would be, we've got to divide the speed of light by the velocity of that light in that particular medium. All right, so we've got a couple of questions that looks like this. So let's go to question number 3 here. Question 3 says light travels through a substance at 1.97 times 10 to the 8th meter per second. What is the index of the liquid, and what type of liquid is it? All right, so we're going to go N equals, all right, speed of light, 3 times 10 to the 8th meter per second. We divide that by the speed of that light in the medium, 1.97 times 10 to the 8th meter per second. All right, we'll put this in. Again, 3 EE8, that's 3 times 10 to the 8th, divided by 1.97 EE, what was it, 8, equals, comes out to give us an answer of 1.52, and I'm going to round it off 3, and you'll see why in a second. Because it says, what type of material is it? What's the type of liquid here? Well, if our value is 1.523, boom, we're looking at crown glass. So I'll put on here crown glass, and we have those answers taken care of. Let's do, how many questions do we got here? We've got 9 questions. So I'll do one more with you, and then I'm going to have you do the rest of them on your own. All right. So let's see. Let's just do number 4. It says, what is the index of refraction of a refractive medium if the angle of incidence in air, all right, air is 1, we have the angle of incidence is 30 degrees, and the angle of refraction is 15 degrees. Good, this one will give us a little different look. Snell's law, 1, index of refraction of our first material, times sine 30, which is the angle of incidence in that material as it strikes the boundary, equals, we do not know the index of refraction for the second material, so I'm going to put n down for it, times sine, what I do know is that it's 15 degrees as it exits that boundary into that second medium. All right, so in this case, we have to divide both sides by sine 15. So we'll put my calculator. We're going to go 1 times sine 30, close it up, divided by sine 15. Why am I not doing the inverse sine? Because I don't need to find the angle. I don't need to find the angle. The only time I use inverse sine is when I need to find the angle for it. Well, it equals, so n, the index of refraction here for this one, is 1.9, and let's go to 2 places, 1.93. All right, these are all kind of easy. They're pretty fun. When you get down to number 9, you really have to keep yourself organized here, because the angle that it goes into the flint glass and then into the water and then into the diamond and so forth, if you get one of those wrong, all the other ones are wrong. So let me set the first one up for you. We know that this angle right here is going to be 20 degrees. All right, so, and the first material that it's in is air, and it even tells you right here that the index of refraction is 1. So I will have for the first one, 1 times sine 20 equals, and then the index of refraction for the second material, the thing that it's going into flint glass, is 1.61 times sine theta. We don't know what that is. All right, but I do know that since I'm trying to find the angle, I'm going to start with inverse sine. I'll go 1 times sine 20. We're going to say divided by 1.61, close it, and hit enter. I know that the angle that it's going to be entering into the flint glass will be 12 let's go 2 places, 27 degrees. Okay, so the second part, we know that the angle that light is passing through the flint glass is going to be that 12.27. Once it strikes the water here, that angle is going to be 12.27 degrees off of the normal. All right, we're going to use that existing angle to help identify the angle of refraction that's going to occur as it passes from that flint glass into the water. All right, now if you need to, go back and listen to that again. Do it a couple times if you have to, but understand that the light went from the air at 20 degrees. It entered into a denser material, so it bent towards the normal. Now it's at an angle of 12.27 degrees. It's now going to enter into something that is less dense. We know that the angle of refraction is going to have to increase some. I might be exaggerating how much that is, but it's going to increase. But how much is it going to increase by? You need to use Snell's law to figure that out. We start with the angle of incident. That's this guy. Why is it the incident? Because now it is striking the surface right here. And I know that angle is going to be what I had found from the previous question. So we're going to start out. Angle of incident is 12.27, and the index of refraction in that medium was 1.61 times sine 12.27 degrees. It strikes that boundary. And it's going to enter into water that has an index of refraction of 1.33 times sine theta. We don't know what theta is in this case. This is the last one I'm going to help you with. To get the angle, we need second sine. 1.61 times sine 12.27, close it, divided by 1.33, close it, equals the angle. The angle here is 14. I was rounding off a little too much. 14.91 degrees. And sure enough, it increased. So I did exaggerate a little bit, but that's going to be this. So when that strikes the next material, what's my angle of incident? Sine 14.91. And then you can fill in the rest of this. All right. These should be pretty straightforward if you follow those different formulas. And if you have any questions, you can email me, but they are due tomorrow. Okay? Take care. Hopefully that's going to record it all.